Olivia Bethula, and this is my lab report for Lab 1. The purpose of this lab is to demonstrate constant velocity of an object in motion. Important concepts that were used were Newton's first and second law. Newton's first law, in particular, that we're looking at is that an object in motion will stay in motion. Newton's second law, however, is the highlight of this lab because it is the momentum principle. It is also the equation of force equals mass times acceleration. Please note that acceleration is the change of velocity over change in time. However, since the purpose is to demonstrate constant velocity, acceleration will be 0, and if we were to multiply that by the mass, the force would be 0. So this iteration process is something I want to highlight because it is something that we are going to use in the computational model. And again, I want to really emphasize the reason that we were using Newton's second law, and notice that F net is equal to the mass times the change of velocity over time. And if there's no change in velocity, it would be 0 times mass equals 0, making F net to be a total of 0. And the main result of this lab is that the object does indeed present a almost perfect velocity, constant velocity. And I say almost perfect because this is a real world, and though we are saying some forces are negligible, that does not mean they do not exist. So again, like I mentioned, the forces that we do not account for are air resistance and friction. Even though we're trying to make a perfect scenario, these still exist. So the outputs of this lab is that, notice the graph, this is the change of position over change of time, and this is also known as the velocity. Well, the slope of this graph is known as velocity, and it is a positive upward direction, and it does not change. And notice that the marker is moving in a rightwards direction. And since the slope of this graph is not exactly perfectly straight, but it does not change, you can say that velocity is constant. Now, when it comes to the computational model, these are the initializations that we set. The position vector was the same position vector as the observational model, and the velocity was taken from the first two positions over that change of time, and we set that to be the velocity. And then this is our actual loop where we conduct our calculations. I set F net to be the vector 0, 0 because that is what we indeed want. And the rest of these calculations are simply a redundance of the position and velocity update. And these are the outputs that we received. So as time increases, the position also increases. And since velocity is a change of position over change of time, it is a positive upward non-changing slope. Hence, velocity is indeed constant, and it proves it right here in our model. And if we were to compare the observational and computational models, you notice that the observational model is less straight than the computational model. However, both demonstrate a constant slope or a non-changing slope, and proving that it is a constant velocity, though the computational model does a better job at it. So possible errors that could have occurred during this experiment was the way we tracked our information. I was the one who collected all the data in my video, and I am human, so it is possible that I made errors when choosing the points that along the axis as the object was in motion. Another point would be having those forces that were negligible. They still exist. And now when it comes to the more questions, what if the axis of our model changed? So when that happens, the velocity components would change. However, they would just be expressed differently, adjusted to the new frame. However, the magnitude of the velocity does not change itself, and it will remain constant. So, and the velocity components, again, will change proportionally. So you ask ourselves, is it possible to understand how many pushes and pulls are being added together to equal zero net force? This goes back to saying the forces, this goes back to saying and highlighting the forces that were negligible. We need to take into account the pushes and pulls, meaning we need to take into account the horizontal forces and the vertical forces, and we need to make sure that there are they equal zero in of themselves. We need to think equilibrium and have an expected result of the magnitude 0. I hope that made sense. In conclusion, we did demonstrate that It is possible to have a constant velocity of an object that is in motion as long as it is in a straight line, whether it is upwards or downwards, regardless of the axes that were changed. And we highlighted important concepts such as Newton's second law and first law, especially Newton's second law, as it was demonstrated both in the computational and observational model. Thank you for listening.